Hello and welcome to a concept review module on statistics. This is part one of a two-part module. This one covering basic statistics, part two covering more advanced statistics for geospatial technology. I'm Ann Johnson, Associate Director of the Geotech Center, a National Science Foundation grant that is helping colleges prepare the geospatial workforce. This concept module will define and compare the word statistics and geostatistics and review some important basic terms and concepts. It'll include descriptive and summary statistics, standard deviation, variance, correlation coefficient, and look at some normal distribution, bell curves, and skewness. Also, we're going to review how you classify your data and how you visually present that data can influence what the same data means to everyone. Statistics definitions, here's two of them, one from the online Merriam-Webster, and it's a branch of mathematics dealing with the collection, analysis, interpretation, and presentation of masses of numerical data. And as we know, geospatial statistics does have masses of data. The second one definition is from ESRI, a developer of geospatial technology software. And here it's looking at the difference between standard statistics and geostatistics. It has to do with the location of that data. Some common terms: mean, median, and mode for statistical operations. So the average calculated by dividing the sum of the number of values in a data set. And for a lot of the topics in this concept module, I'm going to be looking at fabulous coffee houses. It's a fictitious set of coffee houses and a fictitious set of counties, but we're going to look at how collection of that data about the coffee houses can be analyzed. So if I say the average number of coffee houses per county are 8, 5, 4, 3, 7, 6, 9, 5, 8, and 7 per county, I can add all those values together. I get 62. If I divide by the number of counties, which is 10, I get an average of 6.2 fabulous coffee houses per county. Mean is the value of a set of observed values halfway between the highest and lowest value. So it's the value of an ordered list. And if I put my numbers in an ordered list, I can look at the positional average of that data. So 3 to 9 are my values. The lowest is 3, the highest is 9, and the median is 6.5. Fabulous coffee houses per county. Mode is the value that appears most frequently in a set of numbers, and for this set of numbers there are 3 values that occur most frequently, 2 each for 5, 7, and 8. So this is actually classified as a trimodal mode. Descriptive statistics are used to summarize the data and the numerical values in your data set, and they're simple summaries. Sample size, we looked at previously, maximum and minimum values, the mean, variability or dispersion. We can look at standard deviation. We can sum them all together, and we can find the range of values. When you're doing a geospatial analysis, you really should look at and review your descriptive statistics. Here's a little bit more complex term, standard deviation, and there are really two methods and two ways to symbolize standard deviation. One is using the Greek letter S or sigma, and that one is for the entire population. So if you know that you have collected all the data about every fabulous coffee house in the county, that's the total population. But what if you think you only have a sample population? Then you use the English S for sample population. The sigma quantifies the variation of set of variables for that total population. And if we look at the sigma and we just take our same values that we've used before, the X to X2, X3 being representing our 8, 5, etc., our mean value was 6.2 and the number is 10. If we use the equation for standard deviation, and it is the square root of that sum of all those values minus the mean squared, the answer is 1.833. If I look at the subset of the total population or a sample population, I'd use a similar equation, but instead of dividing by 10, I divide by 10 minus 1, so the number of values in my data set minus 1, and I get a slightly different number of 1.9322. A low value suggests the values are really close to that mean or the average of all values. A higher value suggests their values are spread out over a larger range of values. There's a really good tutorial on how to use calculations from this website. Also, mathematical symbols. A lot of times people see these equations and they're put off by what the symbols mean. And this is a really good Wikipedia list of mathematical symbols. So variance is how far observed values for one variable in a data set are spread out from the data set's average value or mean, and we found the mean at 6.2 previously. So I look at the standard deviation and I square it. For my sigma, I had 1.9322. For my S, I had standard deviation, I have 1.833. If I square those two numbers, I can see that my average variance for those two populations are between 3.7 to 3.3 per county. Sometimes we want to look at how things vary statistically with other factors. So statistical dependence versus independence. If you have two or more variables, and here we're going to look at fabulous coffee houses per county and hamburger havens per county, and see if there's any dependency between those two variables. So dependency, when one variable changes, the value of the other variable also changes. If they're independent, one variable can change, but it has no effect on the other. So if we find that coffee houses are only located in places that have hamburger havens within 1 mile, this sounds like it is more of a dependent rather than an independent relationship. Correlation coefficient, and you'll see it as the little r, its relationship. So if I have two variables, can I describe the relative strength of that relationship between the two variables? It is calculated by summing the multiplied standard deviations of the two variables, here symbolized by x and y, minus its mean and dividing by the number of observed values. So that was 10 minus 1. And here I have an equation, and it looks even a little more complex than the other one. So our r, but x is just our coffee houses, y is our hamburger havens, and I take the mean of each of those, multiply them together, and divide by minus 1. Calculation of r gives you a value between minus 1 to 1, where r of minus 1 suggests one variable increases proportionally as the other value decreases. 1 suggests that one variable increases and the other variable also increases, and an r value is near 0 suggests there's no relationship. This relationship can also be shown graphically. Here's a good tutorial for R from the Khan Academy. We're going to look at a Khan Academy graph explanation. So this is just 4 of our coffee houses and 4 of our hamburger havens. So if I look at this data set, the mean is 2, and it has 2 standard deviations of x and y. The number of values are 4, and the r is 0.946. That tells me it's close to that value of 1. It probably indicates a relationship. So here's my equation again. And if I look at the graph, it has a positive correlation, a relationship between our coffee houses and our hamburger havens. If it was a negative relationship, then the slope of the line would be going down. Again, the Khan Academy has some good examples of how to graph these. We're going to look at another data set. This is household spending on internet services per month in the United States. So sounds like the whole population, right? So it's Greek letter sigma. If I take all of that data and I put it on a graph, I can get a nice standard deviation of frequency versus how much spending per percent of the population. So at 68% of the data is found between 1 sigma plus or minus, and that is 90 to 110. So it's telling me that most 68% of the US population spends between $90 and $110 per month on internet. So tell me, how many percent of households in the country spend between 80 and 120 on internet per month? Take a look at the graph between 80 and 120. Sometimes you can get a data set exactly the same mean or average, but very, very different sets of data. So we want to look not just at the mean, but also the spread or the variance between those two populations. Here's a graph of two populations, both of them with an average of 100. One has a standard deviation of 10. The other has a standard deviation of 50. And I can see by the graphing the data that it's one data set is really spread out where the other is very close to the mean. Skewness is mean, median, and mode. And if I graph that data, I get a very different curve than that nice bell-shaped curve. And it means that the data is not evenly distributed around the mean, and it's skewed to one side or another of the data set. On this particular one, the solid blue curve has a very low sigma 0.25, which suggests the observed values are closer to the mean, but are still skewed a bit. The dashed purple curve is really skewed, right? It really shows that there is the mode occurs on one side, the mean is in the tail on the other side, and I can see my data is really skewed. Numerical values of an analysis can be grouped or clustered in various ways, and some of the ways are quantile or dividing into 4 equal parts, or I could divide it into equal intervals, dividing equal numbers of values per desired number of intervals, or I can use standard deviation. So I can take that bell curve and do the plus or minus 1 sigma, 2 sigmas, 3 sigmas. Now that we've reviewed some of the basic statistical operations, let's look at applying it to visualization or mapping that data. So I'm going to look at those fabulous coffee houses data set again graphically. And each of the values represents the number of fabulous coffee houses in a county. And the data can be used by county polygons. So I'm going to visualize the different classification schemes and look at the visualizations. And really what I would like you to see is that depending on how you graph that same exact data, you really can have a lot of information or somewhat misleading data classifications. If I just do random colors, it really doesn't tell me much, right? What's the difference between the 3 and the 9? Not too much. If I do a color ramp, I can see the low values to the high values. Light usually means less values. Dark usually means more values. A little more information. I can look at standard deviation. So I can really see that that 9 is quite a bit from my mean of 6.2, but I can see that 3 is very low. Not sure exactly what it's telling me, but if I normalize that data by the area of each of the polygons, where 3 didn't look like it was very valuable, when I see it graphed, though, using standard deviations and normalized by the square mile of each of those polygons, must be a city because they have 3 in a very small area. So this one I think tells you more. The modifiable area unit problem is one that see a lot of data, especially if it's by state, where the perceived results and maps can be very different or lead to other different types of interpretations. So if I take my same data and I use a polygon size of state, I see one version of it. If I take it by county, I really get a very different feeling. And of course, by census tract, unless I'm going to zoom in, it's hard to see anything, I get another one. So really a color ramp with dark red populations per square mile with different areas really gives you a different interpretation of your data. This is a 2-part concept module, and this is the end of part 1, and it reviews the basic statistics for geospatial technology. Please do continue on to part 2, which is a review of additional topics more on advanced geospatial statistics for geospatial technology. Hello, please see the Geotech Center website for more concept review modules, and of course the one for part 2. If you need more detailed help, there are model courses on the various topics, and they are also on the Geotech Center website. If you have any suggestions or corrections for this concept module, please do contact me. Thank you.